through the other proof by contradictions. I'll do 3 in this video and 3 in the next. So we can get right to it. I've already introduced what proof by contradiction is, just like a brief overview. Step 1, stating what you want to prove. This is just like given in the question. Step 2, assuming the opposite. So that's called the negation. Even is odd, positive, negative, rational, irrational. You derive a contradiction. You do this algebraically or however you see fit. And then step 4, you do this standard statement that's given. You're always given a mark for this. It's the same for every question. This is a contradiction, therefore our assumption was false and the original statement is proved. Okay, so we can get to it. Proof 1, proof 2. Okay, let's do proof 3. So proof 3 is prove by contradiction if n squared is even, then n is even. Okay, so first thing, so this is obviously our statement. Our step 2, you can assume, if we're doing a contradiction, we can assume that n squared is even, then n is odd. So this is, like I said, the second step. This is the negation. So instead of saying if n squared is even, then n is even, we're saying if n squared is even, then n is odd. So this is like the opposite. So now we go over simple things. So if n is odd, you should know that writing an odd integer is always 2 lots of something plus 1, because obviously an even number plus 1 is odd. So 2k plus 1, I'll say that n is equal to 2k plus 1, where k is any integer. That's fine. I've just represented n as odd, like represented in another way. So now we can figure out what n squared is. So n squared, 4k squared plus 4k plus 1. There we have our n squared. We can write this in another way. Let's say we factor out 2 of the first 2 terms. 2k squared plus 2k plus 1. So here we see that n squared, before I said an odd number, is 2 lots of something plus 1. So here our n squared is odd. However, our n to begin with was odd, but our n squared is even. This and this cannot be true at the same time, because we've just said that, and we figured out n squared is odd, but we said it was even to begin with, so this cannot be possible at the same time. So we can write, this means n squared is odd as it is 1 more than a multiple of 2. And then we could say, but we assumed n squared is even. This is a contradiction. Contradiction. So then we can just write, therefore, our standard statement, therefore the assumption is false by proof by contradiction. And then I can just say, if n squared is even, n must be even. It's the only way it works. And we can prove this like, if n squared is even, n must be even. If you have 4k squared, it's even. If we say that's n squared, then n would just be 2k, which is also even. So you can see a little example that it works. Okay. The fourth one, proof 4. This is a nice one. Okay, this one isn't really standard, but these kind of things you should know to do with rationality and irrationality. So prove by contradiction that irrational minus irrational is irrational. This is just, you can see this one through common sense, because let's say I had rational minus irrational, let's say 2/3. This will give us irrational, because it will give us ending with something with 0.666, or sorry, 0.3333. So if we want to prove this, we can just say, well, we do a contradiction first, or our negation. So we can assume that, let's say, an integer a, or not an integer, but a is rational, and then we introduce another variable, b is irrational. And then we say, but a minus b is rational. So this is our statement I'm trying to prove wrong. So if a minus b is rational, let's call a minus b equal to another thing, t, where t is rational. That's fine. And now we can do some rearranging to prove that the statement is wrong. For example, if I move the b to the other side, we get b equals to a minus t. Okay, so now if a is rational and t is also rational, then b must be rational, because any two rational numbers give you a rational number, but we said b is irrational over here. So there's a contradiction. So if I just write this formally, since a is rational and t is rational, and then I can say a little statement which you can say to show that you know what you're talking about. And rationals are closed under subtraction. That means a rational minus another rational will always be a rational under subtraction. A minus t must be rational. And we can do our contradiction, but b is irrational. This is a contradiction, since b cannot be both rational and irrational. Okay, then I can just do our standard statement. Therefore, our assumption is false and a minus b must be irrational. There you go. One more left for this video. Okay, this is a nice one. Proof 5. Root 2, prove by contradiction, root 2 is irrational. This is a standard one. Maybe your teachers have showed you this before as a example of why root 2 is irrational. So our contradiction is quite easy to see, or our negation. Assume root 2 is rational. That's fine. So then now if we say root 2 is equal to p over q. Now this step's important to understand. We say root 2 is equal to p over q, where p and q are integers with no common factor. So this means p and q are in their simplest terms. So for example, 2 over 3, you can't simplify that. P and q cannot be numbers like 4 and 6 or 9 over 18. You can't have these two, because obviously common factor, so they cannot be represented as that. Okay, next step. This is just like, you just have to learn this. We can just say if I square both sides and move the q squared to the other side like that, we can say therefore p squared is even, which means p is even. This statement is actually our proof. Our proof 3. Yeah, if n squared is even, then n is even. If you're using a proof in a proof, then you don't have to prove that proof. We just assume that this proof is true. So if we say this, then we can say, we can write p equals 2k for some integer k. So p squared equals 4k squared. So that means 4k squared is equal to 2q squared from our above, because p squared is equal to p squared equals 2q squared, which means that q squared equals 2k squared. Now here's a contradiction. If we say if q squared is even, then q is even. But we said that p and q have no common factor, but if they're both even, they obviously must have a common factor. So we can write our statement: both p and q are even, so they share a common factor of 2. This contradicts our assumption that p over q is in lowest terms. Therefore, root 2 cannot be rational, so root 2 is irrational. And that's it. Okay, there we go. So that was it for this video, guys. We've gone through 3 more proofs. We have 3 more left. So we have proving that equation has no integer solutions, proving that a quadratic has no integer solutions, and then proving if something's a multiple of a number, then if the proof is if n squared is a multiple of 3, then n is a multiple of 3. And then we would be done with proofs, and then we will go on to the next topic, which is functions and graphs, I believe, from pure year 2. So yeah, okay, I hope you enjoyed this video. I'd really appreciate if you like and subscribe, and I will see you guys in the last part of proof by contradiction. Bye.